All right, I call this part 8B of our notes. So essentially, part A, we talked about vapor liquid equilibrium. So in this set of notes, it'll just walk through an example problem involving VLLE in terms of constructing our phase diagram and then doing analyzing a simple problem using that VLLE phase diagram. And so it's not really anything unique or new, it's just an example. And I will apologize in advance. For some reason, my plots, the axes labels aren't coming up in my slides, but nonetheless, we'll talk through it, and I think it's still okay in terms of being able to follow along and understand what's going on. Okay, so again, it's just an example problem from essentially the material from part 8 of our notes. So we have an example problem where we're told the system 2-butanol in water at 1.013 bars, or that's 1 atm, exhibits partial miscibility. Data for the system are given below. Answer the following questions, neglecting the variability of mutual solubility with temperature. All right, so we'll come to this point, but it'll just be when we identify our mutual solubilities in our bubble line, we'll just draw some vertical lines down for our LLE phase boundary and just assume those compositions are constant at the boundary. Okay. So part A, make a TXY graph and annotate single and two-phase region. Okay, so before we do that, we'll look at our plot from before. Okay, and so remember, I've got my standard VLLE diagram up here. So here's my dew line separating my vapor from two-phase region. Here's my bubble line separating liquid from two-phase. This is a system with it's a heterogeneous minimum boiling azeotrope and has this characteristic flat region of my bubble line. All right, where those 2 points again correspond to my mutual solubilities. And yeah, okay. But this top part is what we're going to try and construct via the data provided in the table. And then the piece of information provided in the problem statement that it says assume the mutual solubility is constant with temperature just means when I construct this LLE region, once I've identified these 2 points, I'm just going to draw vertical lines straight down. Okay. All right. So this is X or Y versus T-bubs and T-dew. So the way this works, again, is I'm going to plot T-bubs versus X. I read X from my bubble line, and I'm going to plot T-dew versus Y. Right? I read Y's from my dew line. Okay, and all I've blocked in here is, I noticed that the bubble point temperature is essentially constant for this range of compositions. That's going to correspond to my flat region of my bubble line. Okay, and then this would correspond to those 2 endpoints, which would correspond to my 2 mutual solubilities, 0.04 and 0.48. Okay, again, I apologize because my axes disappeared. Okay, but this is temperature, and then this is mole fraction going from 0 to 1. Okay, so red, all right, this is just T-dew plotted against Y. Black is T-bubs plotted against X. Okay, and then I see this flat region here. This is that 0.04 and 0.48, that range that was just highlighted. And here we have our azeotrope. Okay, so there's my bubble line and dew line. Okay, again, below my bubble line I have a liquid. Above my dew line I have a vapor. And in between, two-phase. Okay, so what's the significance of the horizontal section of the bubble line? Remember, this flat region indicates that my binary system is going to be partially miscible. Okay, and so what that means is if I look in this liquid region, okay, that below my bubble line, I'm going to have partially miscible liquids, right? I'm going to have 2 partially miscible liquids. Okay, the 2 endpoints, right, where I go from flat to being curved, correspond to my mutual solubilities. So this would give me, if I had a mixture of this liquid mixture of this composition, I heat it up to my bubble line, right? Have this liquid in equilibrium with that vapor, right? So this liquid is going to be rich with respect to component 2, right? And so we would say, call it a mutual solubility. It gives me the solubility of component 1 and 2. Okay. If I'm to the right-hand side and I heat up to my bubble point, in this flat region, I have that vapor in equilibrium with this liquid. And so that's going to give me, I still call it my component 1 rich phase, even though it's 0.48 mole fracs. But this would give me the solubility of component 2 in my component 1 rich phase. So in the problem, we're told neglecting the variability of mutual solubility. Okay, so all that means is when I draw my LLE phase boundary, I'm going to assume that the composition of those two phases is constant, and so that just corresponds to then drawing just vertical lines downwards for my phase diagram. Okay, where this would be 0.04 and 0.48, if I recall correctly from the tabulated data. Okay, cool. So now B, you're given 1 mole of a mixture that contains 2 butanol and water at 1 atm, 75 degrees C. The system consists of a single phase, but its composition is not known. You add water dropwise at 1 atm and 75 degrees C, and you notice a tiny amount of second liquid phase appears when you've added 0.46 moles of water. What was the composition of the solution you started with? Okay, and so, just graphically, what this means is, okay, so again, I apologize for my axes, but if I just go to the table, right, this is for butanol water, right? So component 1 is butanol, component 2 is water. So if I start with a system of 1 mole that's, of 2 butanol and water, and it's a single phase, and then I'm going to add water dropwise, okay? So if I have a single phase, what that tells me is I'm going to be somewhere over here, okay? So this is my liquid-liquid phase boundary. To the right of my phase boundary, I'm going to have a single phase, okay? And why I know I'm over to the right is, over to the right, this would correspond to having a butanol-rich phase, okay? And we're going to add water dropwise until we end up forming a 2-phase mixture. So what that tells me is I'm over here in my butanol-rich phase, and when I add water, what that corresponds to is decreasing the composition of butanol. So what I'm looking for is, I'm going to decrease the composition of butanol until I hit my phase boundary, at which point I form 2 partially miscible liquids. Okay, and so, the temperature is just going to tell us that we're below this, horizontal region or bubble line, so that we're in the LL region. And I start with the mixture. I want to know this initial mixture composition, right? It's just 1 mole total. When I add 0.46 moles of water, I'm now at this new composition here, which would be 0.48 mole fractions, the composition of this phase boundary. Okay. All right, so composition, at the point at my phase boundaries, 0.48. And so what I want to know is the mole fraction. Essentially could use Z. Here I use x1 naught of that mixture I started with. Okay. So if I initially have 1 total mole and I add 0.46 moles of water, right? So my new total number of moles is 1.46 moles of water, so that the final mole fraction is 0.48, right? I could solve for, this would be the initial number of moles divided by 1, the total number of moles in my initial system. So if I solve for x1 naught, right, I get x1 naught is 0.7. So I started with 0.7 mole fractions of water, or of butanol over here, and I had water dropwise till I hit my phase boundary. Okay. C, 20 moles of 2 butanols mixed with 80 moles of water as the system is brought to boil until 75 moles is in the vapor phase. How many phases are present at this point, and what is their composition? Okay, so all this corresponds to is, okay, the initial number of moles, or the initial composition of my mixture is 0.2. Is, I need to know where I am in relation to my azeotrope. Okay, so if my mixture, if my Z is less than the mixture of my azeotrope, if I'm to the left of my azeotrope, when I heat up into the 2-phase region, I end up in this side of my phase envelope, okay, this lobe. So if my Z is less than my azeotropic composition, and I heat it up to the 2-phase region, I get phase splitting, right, where I have a vapor of this composition and equilibrium of liquid with that composition, right? So I have, vapor phase, right, where Y1's greater than Z, in equilibrium with this liquid, where I would say this is my component 2 rich liquid, which in this case would be my water rich liquid. Now if I start with a liquid mixture, which is to the right of my azeotropic composition, and I heat it up to the 2-phase region, I'm going to end up in this lobe. Okay, in this lobe, what I find is that my Y1 is going to be less than Z, is going to be less than X, right? And so I'm essentially going to concentrate component 1 in the liquid phase, right? It's X1's greater than Z. Okay, and the trickery that this problem is just trying to get at is, what we had discussed before, right? If I were to draw a drop-down line at this azeotropic composition here, okay, if I have a mixture of this composition, right, I'm still in my two-phase region, my LLE region, and I'll get phase splitting, okay, along that isotherm. But if I heat it up to the two-phase region, right, which lobe I end up in depends on my overall system composition. So if my overall composition Z is to the right of my azeotrope, right, I essentially have, you know, a liquid, right, that I'd say is rich in component 1. I have this liquid that was so at this point, right, this liquid is still in equilibrium with this liquid. Once I hit my bubble point, this liquid disappears, right, and I'm left with this liquid in equilibrium with a vapor. Okay? And so, you know, the game that this just gets at is if I'm in my two-phase region, I have two liquids in equilibrium, but now if I'm to the left, these two liquids are in coexistence. As I heat it up to the two-phase region, this liquid's going to disappear, right, and I'm going to be left with this liquid in equilibrium with a vapor phase, right? And that's all that this game is trying to get at, where, you know, here's my overall mixture composition, right? And so if I just remember what Z is, that tells me what lobe I'm going to be in, and it tells me what, you know, liquid I have in equilibrium with that vapor, right? So this would be a component 2 rich liquid. If I were over here, we'd call it a component 1 rich liquid, okay? And, you know, that's all it is. You know, this one we have to play around with lever rule in terms of exactly knowing where we are on that line, okay? And, yeah, you know, that's essentially it. You know, last piece is just even if I'm in the liquid region, if I want to know how much liquid or how much of each liquid phase I have, you would still tackle it essentially as a flash drum problem. So if I know that I'm below that horizontal region of my bubble line so that I'm in the liquid region, but I want to know how much of each liquid phase I have, right? You could do a flash drum analysis. Here, we're going to have a mixture that's 82% 2-butanol. This could be flashed at 1 atm. And desired mole fraction of the flash separator is 98%. Determine the temperature of the separator and the amount, right? And so, you know, so if I want to know the amount of the two liquids, I can do the same flash drum below that horizontal region of my bubble line. Here, though, this is just our standard flash problem as we did before with TXYs, right? And it's just a matter of keep in mind, you know, even if my mixture is partially miscible, all right, just remember that Z that's being sent into the drum at which I'm pulling out liquid and vapor, right? So I'll leave it at that. You can look at the notes in terms of going through some of the particulars.